Hi everybody. So I hope you liked yesterday's videos. I noticed not everyone watched them, so that's confusing. Not sure how you're going to get the work done if you're not watching the videos, but stuff is being assigned. Just so you know, I'm assigning the rest of 2-5 today. So I do want you to do all of those problems. I'm going to finish going over the lecture notes, okay? I have mentioned already in the earlier page that any time that we had a sharp corner, which is any sort of absolute value function, right where the vertex is going to be a problem for us to find the derivative, because we can't draw a tangent. Like if I try to draw a tangent, there's one there, there's one there, there's one there, there's an infinite number of them. So I'm going to turn here then and look right at this first problem on page 36 and say, hey, that's absolute value. I know the vertex of the basic absolute value is at 0, 0. So if I'm trying to tell you where it's not where you can't find a derivative, I would say can't find one when x equals 0. Cannot find at x equals 0. And the reason why is I would call it a cusp, or I would call it a corner, and I've also seen people call it a sharp turn. Okay, now I want to look at a piecewise function here. And by the way, I got room, so I'm going to go ahead and sketch that really quick. I know that x squared is this lovely parabola shape. It starts at 0, 0, and it goes up from there. And I'm saying, oops, my bad, I drew the wrong side. I'm saying that I noticed that it was piecewise, and I have to only write down the part where x was less than 0. For the function x, I know it's a lovely straight line where every number equals every number, right? So 3 equals 3, 4 equals 4 in terms of what x and y are. And so right here, as soon as I've drawn this, I've noticed that there is a cusp. There is a corner, there is a problem, okay? And so I would say that I cannot find the derivative at x, cannot, at x equals 0. Again, why? Because of my corner or my cusp. Okay, I do have a hint here though that I can't find it if I actually tried to take the derivative of this function. So it's worth it for me to try. Let me see. The derivative of x squared is 2x and the derivative of x is 1. And so when I look at these two things, they don't match. Don't match. And so that's a hint to you that the slopes are different. So this has a slope of 1 all the time, and that has a slope of 2 times a number, which means that it's different. So here there's a slope, and here there's a slope, and here there's a slope, and those slopes change all the time. If I check at 0, if I plug a 0 into here, well then my slope actually is 0, whereas my slope over here is always 1. So there is my cusp. Okay, so that was just a hint that you could get from taking the derivative directly. Now I'm going to look at number 10 though, and I said, hey, I have a hint. I could tell you that if I take the derivative, which I'll just do really quickly, the derivative of this function, the first part is 2x. Wait a minute, the second part, I take the derivative of x squared, I get 2x, and then I take the derivative of a constant. Whoa, I got 0. So these technically, they match. Does that mean that the derivative can be found here? Well, unfortunately, the answer is no, because again, I can imagine this shape. I know it's a beautiful little parabola where x is less than 0. It's right here. But for x is greater than or equal to 0, I should start at a height of 1, and I should go up from there. So this is a jump. So you kind of have to be able to imagine both of those things, okay? What does the picture look like? If you could see the picture, then you could see that there's a jump. If you take the derivative, do they match? And I kind of need all of that to be working at the same time in order to say that there is a derivative. Now for number 11, I wanted to mention that even though you don't know how to find the derivative of this yet, I will be teaching you that. We can't take the derivative at this time. We do know enough about rational functions to say, hey, aren't we supposed to set the denominator equal to 0? So I should have x equals 0. I should have x minus 1 equals 0. And we're just determining where there are some potential areas of concern for us with this function. Yes, we have determined that 0 is a problematic area, and we have determined that x equals 1 is also a problem area. Now I know that if I factor this, that is a removable whole. Okay, fine. But just because it's removable doesn't mean that I could take the derivative there. It is not continuous. Okay, it is not continuous because there is a hole there with the original function. All right, and then for the second piece, I would say, well, hey, this piece isn't removable, so doesn't it mean that there's some sort of asymptote there? And if there is a vertical asymptote somewhere, then that means that I can't find the derivative of it. Will I be able to find the limit of it? Maybe, it depends on the behavior of it at that point. Is both sides going up to infinity? Are both sides going down to negative infinity? If I could figure that out, I could find a limit, but not a derivative. Okay, so the last piece I will mention that we really need to get a handle on these fraction exponents and think to ourselves that we're going to use that tool every time we try to take a derivative of it. So if I'm going to take the derivative of f prime of x, I'm going to say that 1/3 comes out in front and x has a new power and that power has been reduced by 1. So if I do 1/3 minus 1, this is the same thing as 1/3 minus 3/3, which gives me a negative 2/3. Now, when I want to try and think about this function and whether or not I could take a derivative everywhere, let's get it into the proper format first. And that's why I've been really focusing on you guys simplifying all the way down to, ready, this level. I want x to be squared, and I want to take the cube root of it. And as soon as you see that there's a denominator there, you know that if you set x equal to 0, we have a problem, okay? And by the way, what kind of problem do we have? We have a vertical tangent. All right, we have a vertical tangent, meaning that I wrote down x equals 0. X equals 0 is a problem. Why? Because if I evaluate my derivative, meaning I plug in a value that I wanted to know what the slope was, I would get 1 over, ready, 0. And this is called undefined. If I am trying to divide by 0, there must be, ready, a vertical tangent. Why do I say that there's a vertical tangent? Because vertical tangents have undefined slopes. So the slope is undefined, means no derivative. And I'm going to refer you back, I'm zooming out here, I'm going to refer you back to this picture right here. It looks like that. There's a vertical tangent there because I have an undefined slope. And that undefined slope means that that line must be straight up and down. All right, so now that I have done all of that, you can pause and rewind if there's anything that you need to capture on your paper. I definitely want to make sure you feel like you are looking at this video and taking some time to record everything. So feel free to pause when you need to, rewind when you need to, and now take a break if you need to, then come back. We are ready to talk about rates of change. I have mentioned to you before the average rate of change is a thing that we would like to find, and we call that a secant slope. And we are using the slope formula. But what I had said previously was, what if I want to find out what's happening in an instant, like right away? What if I want to see like at the exact second of 2 seconds or 6 seconds? I've got my rocket ship taking off. What do I do? Ready? We now have this tool that is called the derivative, and we will try to find out what the value of the derivative is at a particular point. Okay, so let's try one, and this one the numbers are pretty big, so I won't lie, I've put some of those numbers into the calculator already and I have them. I can't display the calculator at the same time as OneNote in my videos, so I apologize for that. So hopefully when I say I put it into a calculator, you'll understand what I mean. So if I want to find the average rate of change from x equals 10 to x equals 30, I should probably find out what the value of my function is at 30 and the value of my function is at 10. So I would say that I have something being cubed plus 2 times something, and the somethings just happen to be 30 and 30. And so I'm going to say that on the calculator, I got this number right here, comma 060. Now I want to find out what's happening when my function is equal to 10, and I'm plugging that in, and I say I have 10 cubed plus 2 times 10, and that equals 1,020. Now previously in class, I would have done something like this. Ready? X and Y. I would have said, what happens when X is 10? What happens when X is 30? And let's call this my X sub 1, and this is my X sub 2, and so on and so forth. But we're getting tired of having to make the little t-chart every single time. And particularly, I'll say that if you could do this on a calculator, shouldn't you? Shouldn't you define this function with your f colon with the equal sign, and then you say this is x cubed plus 2x, and then on the next line after you hit enter, shouldn't you plug in f of 30 and hit enter and see what happens? Right? So that's why I'm mentioning that we want to also find out what's happening when f of 10 is appearing. What do we get? And then finally, I will mention on the calculator, if you have defined this function, you could just put in the slope formula. Ready? Don't put in the m equals. The m equals is for you. You know that you are doing m and that it equals. What you put into the calculator is this. Ready? F of 30 minus f of 10. And all of that is over, ready, 30 minus 10. Ta-da! Now, when you get the calculator, you hit the enter button, it will tell you that the answer is 1302. And I'm going to say for you right now that I've seen teachers call this AROC, average rate of change. And it's kind of cute, but I really like it when I write the whole answer out. Average rate of change, because I know you're going to forget. You're going to forget what an average rate of change is if you don't actually write those letters out, write those words out so you remember it every time, okay? But you do you. I'm just saying what I do. For number 14, I'm looking for that instantaneous rate of change, and I'm going to say again, all I have to do is find the derivative. Now, I won't lie, there is a function for finding derivatives on our calculator, but right now I really just want you to focus on doing it by hand. These are all supposed to be easy like that. Ready? X is cubed, so I have x cubed. Power is coming down out in front, turning it into a 3 in front of my x, and instead of having x cubed, I now have x squared. What happens when I take the derivative of 2x? I get 2, and ta-da! If I want to know what the instantaneous rate of change is when x equals 10, all I have to do, ready, is plug in 10. So my answer will be 3 times 10 being squared plus 2, which I did plug into a calculator, is 302. That is my instant rate of change. Okay, and now I believe that you have enough tools to be able to do the homework. I'm flipping over to that page, and I'm mentioning that, I'm sorry, I'm going to be gone today and tomorrow. I know you're going to want help with this. No, I want you to do all of it. Did you see at the top I said I want you to do the whole thing? Here, let me see. Oh, 1 through 48 all? Are you kidding, Ms. Chatra? Yes, I really, really want you to do all of them. Because these first ones are pretty simple, right? They look like, hey, you know, find the derivative. We should use the correct symbolism. I think this is good practice for you, and it should be relatively quick. 17, you're definitely going to want help with. You know what I mean? I could tell that you're going to want help with it. I am already aware of that. For these guys, where there's stuff in the denominator, do you just need me to mark that? Something like this? That would help you with this. This little piece, this is really x to the negative 2 power right here. So I would rewrite this as x squared minus 4 times x to the negative 2 power here. How would I do number 14? Hey, you do know how to distribute, right? Shouldn't we say that g of x is equal to something? And maybe you should try that. Down here for number 20, I do want to point out to you, you definitely need to square that 3. All right, and then let's see if you can't get through more of these all by yourself. And tomorrow I will try to tackle in a video for you, if I can, the ones that I've already mentioned that I know you're going to want to have some help on. What is due on Friday is, let's see, your guys' let's see, your grade sheet 3. So I had already assigned some of the Unit 2 review, and now I am signing 1 through, what was it, 48 all. I am dying for that to be done. Sorry. By 9:28, which is the end of this week, I believe. Nope, 9:27. Okay, 9:27. So you better get to work. You know what I'm saying? I will definitely cover a few questions in class on Friday before I collect it.